guess this will be part B. So, in 3 dimensions, we're going to try to do the same thing. We can definitely talk about the volume. Do you remember what the formula is for the volume of a sphere?
4/3 pi r cubed.
R cubed, okay. And what's the analogy in 3 dimensions to circumference?
Surface area?
Why? Why do you think that?
Well, because the circumference is the distance around the outside of a circle.
Uh-huh.
The surface area is the space around the outside.
Okay.
The circle.
Remember the formula for the surface area of a sphere?
4 pi r squared.
4 pi r squared. Okay, and we're going to try to do the same thing. We're going to try to come up with a 3-dimensional analogy for Patrick Honner's formula. In fact, he did this in his blog post, and we even studied it with a few zone shapes. So what was the formula here?
I think it was surface area cubed over volume squared.
Surface area cubed over volume squared. Okay, so let's see what that's going to give us. What's it going to give us on the top?
So on the top, it's going to give us 64 pi cubed r to the 6th.
Okay, and how about on the bottom?
Be 16 ninths pi squared r to the 6th.
16/9 pi squared r to the 6th. Sorry, I'm running out of room there. R to the 6th. Okay, so we see the r to the 6th canceled.
You have a pi on top.
Okay, and now we just have to figure out what multiple of pi
You
we
have
have.
4, and then you have 4 over 1/9.
Okay.
So we 36.
All right, so this gave us 36 pi. All right, so all we have to do is divide by 36, and we found a 3-dimensional analog
For pi.
for pi, and it helped us because for the zone shapes we looked at, we could find the volume, or if we look up the volume, or if like a cube, we know the volume, we know the surface area, and we can see what this formula gives us in terms of pi, and we were able to sort of identify like how circular something was by how close to pi we were getting. So things like tetrahedrons were not spherical. We're not particularly spherical.
And dodecahedrons were.
Yeah, dodecahedrons were. So that was kind of cool. So now we're going to try to extend this idea to 4 dimensions. Okay?
All right.